reality. What a concept.
Let's do this. Hell yeah. All right. Counting down. 5, 4, 3, 2, 1. What's up, everyone? Welcome to Simulation. We are sitting down with Dr. Garrett Lisi. What's up?
Hey, Alan. Thanks for having me on the show.
Thanks for coming on the show. Greatly appreciate it. So we're going to be talking about physics. We're going to be talking about reality. We're talking about the subatomic level of reality. This is going to be very exciting stuff. I'm pumped.
Well, cool. I spend too much of my time living there, so I'm happy to bring some back and share it.
And try and make it as relatable as possible as well. Like that's definitely something that we care about here, is making complex subjects relatable. And so your background, you had PhD in physics, University of California, San Diego, and then 19 years at the Pacific Science Institute.
Well, it was just an idea for most of those 19 years, but now it's a reality, which is great.
I'm excited to showcase some of the content that we have lined up for highlighting PSI. And what would you even call PSI?
It's mostly, right now, it's mostly a house with delusions of grandeur. But what I'd like to build it into is a larger residential science institute, science retreat, the same way you have retreats for artists or writers. There isn't really an equivalent sort of space that scientists can go through to work on their stuff. And so that's really what I'm trying to build in PSI. It's just a nice place in a beautiful location where scientists can come out and spend time working on whatever they want and enjoying the environment.
And what better place to do it than in freaking Maui?
Yeah. I haven't found any place I like better in the world, so that's why I'm there.
Yeah. So you got a nice property with a couple cabins on it, enabling scientists to come and retreat and work on their research, and in beautiful Hawaii. 20-minute drive from the ocean, up on the volcano, 1,500 to 1,600 feet up. Sounds so great. We'll showcase some of this content soon. Okay, so let's start with this. So we have this. I always like to explain it this way. Humans are kind of they're sandwiched between the macroscopic galactic perspective as well as the micro subatomic perspective. We're like sandwiched.
Yeah, if you look at the scales of levels of magnitude between subatomic particles all the way up to the scale of our observable universe, humans are about in the middle as far as the size of things go. Yeah.
So interesting how that happened.
Yeah.
So when we experience life, we're experiencing life on this, let's just call it on this level of like meters, because things are kind of metric, right? In terms of meters and stuff, like that chair is about a meter, you're about a meter. The whiteboard's like 3 meters, so it's kind of like metric in a sense.
A meter was invented because it's on a human scale.
Yeah, exactly.
It's not a natural unit of measure. It's one that we made up because it's convenient for us to use as humans, because we're about on that same scale.
Yep. And then we go all the way up to hundreds of millions and even billions of then light years, and then down we go to the subatomic level, even as low as the Planck length.
Well, we haven't gotten that low yet. Fortunately for us, space is wonderfully transparent, and we're surrounded by clouds of billions of galaxies in our universe, and we can actually see them and collect data from them and see out extraordinary distances into space because it's transparent.
Yes.
Similarly, we can use particle accelerators, microscopes, and then particle accelerators, which are basically larger microscopes with more energy, to see down smaller and smaller and see how the microworld behaves. And we see incredible richness on both scales, and also sort of different emergent levels, laws of physics on those scales.
Okay, so the laws of physics that govern our world, maybe as we get down to this, the particle accelerator and being able to see what goes on at that level, let's start with about 1500 or so in this Renaissance area time period. We're getting optics, we're getting to see up and see down, macro, micro, And like you said, you started talking about microscopes, so then we started being able to see at the kind of like the bacterial level, about that level. And I don't even know what that is in terms of, is that at the millimeter or is that at the micrometer level?
It's submillimeter, yeah. More closer to micrometers.
Micrometer level, okay. So it's a micrometer level, that's 1/1,000,000th?
Yeah.
That's 1
10 to the
millionth.
-6, yeah.
10 to the -6, so 1/1,000,000th of a meter for bacteria. And then now even a bacteria is made up of atoms, and atoms are made up of subatomic particles. So now we're breaking down a little further. So now when did we first, I guess, even think that, like, okay, well now, I'm moving my hand and now I'm moving atoms, moving
Right. Well,
nitrogen,
that
oxygen.
idea, I think, goes all the way back to the Greeks, where they talked about the fundamental sort of discrete atoms of nature. So that idea has been around for a while, but it often takes we have a lot of ideas as humans about how our universe works before we actually have access to be able to measure at that scale. But very often you can have insights into how things are working, what reality actually is. It's just 90% of the time they're wrong.
Yeah.
But actually, through science, we actually are able to examine these scales at a deeper and deeper level, and then find out that some of those ideas were right. And some of the early ideas about atoms were actually quite insightful and turned out to be correct. Even Newton had a sort of an atomic picture in his head, or I think they were called corpuscles of light, and now we call them photons. But he had the idea that they should sort of come in packets.
That's so interesting.
Before anybody had any inkling of quantum mechanics.
Yeah.
Yeah. So we think it's sort of our job as theoretical physicists to think ahead of our experiments, if we can, and come up with descriptions of nature that might actually be true.
That might be true, and then you get to go test and test the hypothesis. So yeah, it always fascinated me seeing planets orbiting a star and then seeing electrons orbiting the nucleus of an atom.
Yeah.
Yeah.
Yeah, it's similar forces at play. You have the inverse square attraction of the gravitational force, and you have a similar inverse square attraction of electromagnetism between oppositely charged things. So with that, you have similar behavior.
That's so interesting. Yeah. So the positive and negative of the atom, of the electrons and the protons in the nucleus, and then the gravitational pull between the star and the planets. Yeah, that's so cool.
Yeah. And they used to, back when we knew enough to know that matter was atomic, and to get an idea of what atoms are, I think it was Rutherford saw that atoms have nuclei, with most of the mass concentrated in their center, with the electrons orbiting it. And there was this Bohr model of the atom, and it was very much a planetary model where you have the electrons orbiting the nuclei, just like you have planets orbiting the sun, is a direct analogy.
Yeah.
But then we learned that things on the atomic scale are actually very different.
Yes.
And
God, this
electrons
is crazy.
don't orbit like planets. They exist in a potential probability state of like different likelihoods of being at different locations around the nuclei. Yeah. So although they have angular momentum and they have movement that way, they're fundamentally different. So quantum mechanics describes a fundamentally different world on the atomic scale. So really they're not planets. And also, whereas planets all have their individual characteristics and their abundant, their environment and all their own things that make them them, subatomic particles don't appear to be like that. They appear to be perfectly interchangeable things. So one electron is identical to any other electron, except for where it is and how it's moving.
Yeah. So there's both the Earth is much different than Mars, but the third electron and the fourth electron are
totally identical.
And then also the positioning of the electrons around the atom just moves completely differently.
Yeah, in fact, quantum mechanically, they don't even have a definite position.
Yeah.
It doesn't even make sense.
So this is superpositioning.
Yeah, they have a superposition of all their possible positions.
At the same time.
Yes.
But it's still angular momentum moving. It's not just superpositioning around.
That's right.
Yeah. Okay, so Okay, so now we get to when did we even figure out, I guess, that atoms could be broken down into further? When did we figure that out?
Well, I mean, they figured out, like there was like alpha and beta radiation and gamma radiation from atoms. And then they figured out that alpha radiation was actually 2 protons and a neutron clustered together that were coming out for radiation. So there's naturally radioactive material. And I think it was Curie who did some of the pioneering work in radiation that way, and just trying to figure out what the heck was going on. And so I don't remember when the first breakdown was for nuclei being composed of protons and neutrons, but it was a wonderfully succinct way of describing chemistry. Once you can describe atoms in terms of their protons and neutrons, you get the periodic table. And now we have different versions of the periodic table that are even more intuitive than the standard one you may have seen in high school or so. But there are different ways of portraying it that actually are more intuitive. But you get this wonderful, they're like little Lego blocks of how they can be put together. And now through quantum mechanics, we have a really good description of how all of those are formed. So we understand atomic physics really well, even though it gets complicated. Still,
was this the early 1900s?
I think it was around there, maybe even a little bit earlier.
Yeah.
But yeah, it was around there.
Yeah.
And then we started being able to manipulate atoms, and then create fission, and we saw the results of that both in the nuclear weapons for World War II and in atomic energy generation.
And so let's just pause there for a second. So this is taking very large atoms, and this is slowly breaking them down to lesser atoms.
Yeah, pretty much. If you pile enough protons and neutrons together into a large atom, that's an unstable state, and it likes to split. And when it splits, it releases energy.
A lot of energy
by the pieces coming out with more momentum. And we're fairly primitive. But we know that once we have something that has a lot of energy, that it's very hot, and we can run water past it, heat up the water, and then use that heated water to go through steam turbines and generate electrical power.
Okay, so then there's running water, and then the energy from the atom splitting is heating the water, which is then that heated water is powering a steam turbine.
Yeah. It's pretty funny that we go back basically to a steam engine. It might as well be a coal burner, right? As far as what's generating the heat, because it's the primitive ways work. So that's the interesting thing is technological advancement is cumulative. So when you have an advance, it's not alone; it's building on all the previous advances.
Yes.
And this is really what's so fantastic about technological process, because that produces an exponential rate of increase in technological progress, which is great. What makes it so nice to be alive right now is things have progressed at such a rapid rate. It's gotten pretty great.
Agreed. Ubiquity and so many great things that we need. Also, physics is building on top of the fundamentals.
Yeah, we build off what we know, and when we find new stuff, it has to connect and agree with what we already have known and established.
Yep. So now we just did a little bit on fission. Hopefully we can figure out the abundant source of fusion energy. If we can fuse atoms safely for less energy that we took to put in that we can get out, then we can have abundant energy
Fusion
forever.
is fantastic because you don't only have heat being produced like you do in fission, but the atoms involved are much lighter and less themselves, they're not radioactive.
Yes.
So the problem with fusion is it generates so much heat that you can't contain it.
Yeah.
So we can start a fusion reaction, right? And we can get power from it. The problem is it heats up its container to such a degree that it'll melt the container. So we have to try to trap it in a magnetic field, electromagnetic field.
And that's like the tokamak.
Tokamak, yeah.
Tokamak.
Yeah. And these are and it's probably one of the hardest engineering challenges on the planet right now is to build a way to contain an ignited plasma.
Ignited plasma.
Yeah, and to pull power out of this thing. this is one of our greatest challenges right now.
Yes.
Because it'd be a great way to get energy
Yes.
without the same radioactive waste to deal with.
Yep.
It's funny that all these things, it's still going to go back to, based on a steam engine, where use the heat to heat up water and it runs turbines. Yeah.
Is that how we would do with fusion as well?
Yeah. Yeah. Because water is just such an efficient way to transport heat. So because water has a very high heat capacity, it can hold a lot of heat.
Yeah, yeah.
So yeah, you turn water into steam and use that excess pressure to go through a turbine, and then so the water has a dual purpose. You get the power from having turned it into steam, and you're also cooling the generator that way.
Okay, so how did we figure out that we could collide atoms and then understand subatomically what's going on?
Right. Well, studying by knowing the radiation coming out of it. Yeah. And the first experiments were, literally people moving clumps of uranium together with their hands and seeing that it warmed up.
Oh, whoa. It would just warm up? The clumps of uranium would warm up? Because they're trying to what? Electrons are trying to...
They're like, well, that's odd.
Yeah.
Never mind that they just irradiated themselves and they're going to get cancer, but when you don't know what you're doing and exploring this stuff, it's going to be quite hazardous. Yeah. So the early experiments are often quite risky since you're exploring the unknown. And
when was the Large Hadron Collider built? 2011 or?
Before that, they started building it far before that. But I think it first turned on, around 2008.
Okay.
Yeah.
Okay, for first turn on. And so, now...
And then their largest success was finding the Higgs boson, and that was 2012 or so.
Yes.
Didn't that mess with our parallel universe?
Maybe it messed with yours. Mine's fine.
Mine's fine.
You didn't hear anything about that, though? No? Maybe yours.
I do
guy.
believe in other parallel universes in those universes, but not so much in this one.
Wait, you believe in parallel universes in those universes, but not in this one?
Yeah, the me that's in other simulated realities believes in the other simulated realities, but the me in this one, no. Yeah.
Okay.
I'm far too skeptical.
Okay.
That doesn't make sense. Far too skeptical.
Okay, and then China has a massive particle accelerator as well.
No, but they will.
Oh, they're building one.
They're talking about building one.
Yeah.
It's in early enough stage. They haven't committed funding to it yet, but I think they will.
They just built that massive satellite, the radio.
Yeah, China's building some amazing stuff, and I think it's very likely that the particle accelerator that supersedes the Large Hadron Collider will be in China.
Yeah. Come on, U.S. Come on, U.S.
Well, the U.S. had their shot. We were going to build the superconducting super collider in Texas.
Yeah.
That was going to be even larger than the LHC from the get-go.
Yeah.
And that was back in the 90s. That was coming together and it got funding. Is going to happen. The thing is just too big of a target for Congress to exit out off their budget.
Because that's whatever, 10 billion, 20 billion.
Yeah, it was going to be. It had a big price tag.
Yeah.
But I'm very biased since I'm a theoretical physicist, and I want to know.
I'm biased towards science too. I'm so biased towards science.
But the thing is this sort of exploration that you're doing, it doesn't have practical impact for at least 50 years. And most, governments, companies.
But you want flying cars? We want flying cars.
Well, we're going to have plenty of flying cars once we have good batteries. So the batteries are the holdup for flying cars. And we're going to have them. So we're going to have personal quadcopters, and they're going to be fantastic, but you're only get 20-minute rides because of the batteries.
Batteries, yeah. Okay, so now we are colliding atoms, and now so you said we're using similar microscopes, but now it's like electron microscopy, so it's even. Okay, so now explain how you're watching.
Yeah, so
atoms.
If you've seen a scanning tunneling electron microscope photo, they can get much higher resolution than light. And that's because the electrons, have a much shorter wavelength than light has. Okay, with light, you can get down to nanometers for the size of things you can resolve. But with electrons, you can see down even smaller. And with protons, you can see smaller still because they have smaller and smaller wavelengths. And you can put more and more energy in them. And so you don't have access to see what's on the smaller scales. until you can collide larger, more massive particles with more energy. And that's how you see things at smaller scales. And for the Large Hadron Collider, there are similar collisions. So the Large Hadron Collider is colliding protons very close to the speed of light, and then seeing what is produced in those collisions. And it's pretty great the way that works. And there was, someone, I think, embarrassingly enough, I think he was an attorney from Hawaii, from Oahu, the Big Island, from Oahu, not the Big Island, who started a lawsuit saying, no, the LHC might create a black hole that destroys the Earth, right? By colliding these protons at energies higher than they've ever been done before. But the thing is we have protons coming in as cosmic rays all the time and impacting the moon, impacting our atmosphere, and it doesn't turn the moon into a black hole, even though it has higher energy than what the LHC is doing. The problem is, we don't know where those collisions are going to happen, and we want to be able to have the collision take place in a detector where we know what the collision products are. And this is our best window now into subatomic particle physics. So with these larger and larger colliders, the LHC being the largest one, we're able to see what the fundamental building blocks are of atomic nuclei, which it turns out are made out of quarks. They're made out of up and down quarks of different charges. And so we now the same way we had the Lego building blocks of atoms, now we have the same building blocks of subatomic matter, of the quarks, electrons, neutrinos, and the electromagnetic weak and strong forces holding them together. Yeah, it's pretty, and it's really, amazingly enough, things are really pretty down there.
Yeah. Is this a good time to pull up the E8 video?
Sure.
Yeah.
Sure.
So
if you plot out all the charges of the known elementary particles, they make a really pretty pattern. You just plot one different kind of charge along each axis, right? And then you end up with a multi-dimensional charge structure that you can rotate and see all the pretty patterns in it. Yeah.
Okay, so what we're observing then is we're observing the quarks, neutrinos, charge patterns. We're observing that right now.
Right. So this is basically a diagram. So if you take the different particles have different charges. So the up and down quarks have charges of 1/3 and -2/3, and an electron has an electric charge of -1. Right? And you can multiply all those by 3. It's just a matter of scaling. So they all have integral charges. Okay? But then these particles also have weak charges, right? Which is a different kind of charge than electric charge. And then they also have 2 different kinds of strong charge, right? And physicists call this color for reasons.
So there's strong charges, weak charges, negative charges, positive charges.
All right, so there's electric charge, there's weak charge.
Weak.
Color charge actually is 2 orthogonal kinds of charge.
What is color charge?
Color charge, yeah. And that's the name for the strong force charge.
Okay.
So strong force charge takes two different kinds of charge to describe, but they interact. Okay, but you also have gravitational spin is another kind of charge for how these rotations interact with gravity, right? And you need 2 charges for describing gravity. Okay, so that gets you up to 6.
This is per subatomic particle?
Yeah, and each particle has some charge along all 6 of these axes. And you plot out each different particle state.
But is each particle the same 6?
Yes,
it is.
Each kind of
is
particle.
The same. Yeah. Okay.
So an electron has the same charges as any other electron.
Cool.
Okay. And so you plot out about all these axes, and you end up with this diagram in 6-dimensional space or higher dimensional space if you add more charges. Okay. And then you can project that down to 2 dimensions, and you see it makes a really pretty pattern.
Okay. Okay. So you take the 6 variables that you were just discussing, and then you put that onto a 2-dimensional.
Yep. You just flatten it down to 2 dimensions, and it shows plots like this. And all this is doing is it's taking that fixed pattern in higher dimensions and projecting it down to 2 with different angles to show different aspects of it.
Yeah.
And each one of these points corresponds to a different kind of elementary particle.
Yeah. Okay.
And since you have charge conservation, these diagrams describe how all these elementary particles can interact, because the charges have to be conserved.
So the purple is an elementary particle, the orange is an elementary particle, the
Yeah.
yellow
Each
is...
one corresponds to a different state,
and
different kind of elementary particle.
And this is all one atom?
No, it's not an atom. This is just one charge diagram
This is a charge diagram for what, though?
for everything,
But what do you mean for everything?
for every known elementary particle.
For every but for every known elementary particle. But what are they orbiting? What are they part of? What is the
It's part of. It appears to be part of one structure.
of a structure?
Yes.
And we don't. And then so this is just replicated throughout everything.
Right.
Just-
So at every point of space-time,
yeah.
you'd have any collection of any one of these particles at that point in space-time. So it appears that
Yeah.
this thing can
Got
be
it.
excited along any of these particle directions at every point in space-time, and this is why there's a particle there.
Okay, so now we go from this is a sea of atoms to now this is a sea of elementary particles.
And many of these particles will cluster together and form atoms. So an atom is basically a bunch of up and down quarks, and in more or less one close location. Okay, being excited and self-interacting with a bunch of gluons, which are the force particles of the strong force. Okay, and that holds everything together with electrons in a cloud around them, all in more or less one spot. So it's a bunch of these particles getting excited all in one location, and then that happens everywhere at every point in space-time, and the interaction of this whole swarm of elementary particles gives us the universe we see.
How do elementary particles figure out to come together with the gluons to make a oxygen or to make a nitrogen or carbon?
It has to do with how the other particles interact with them. So once you know a particle has a charge, right, and what its charges are against for all these different kinds of charge, then you know how it can interact with the other particles, because it can have any interactions with any other particles as long as the charges are conserved when they have the interaction. So you can just basically add the charges and see if that's another particle, and if it is, that's a possible interaction. And every possible interaction happens. Okay, so all these possible interactions are happening and allowed by charge conservation. So everything happens, and also energy and momentum conservation, and all those interactions happen. And as far as we can tell, quantum mechanics describes every possible interaction happening.
Yeah.
So we're sort of living in this branching out of all quantum possibilities of all elementary particle interactions.
Yeah.
Yeah.
And then now we're trying to identify the elementary particle interactions.
Yeah.
Trying
So
to
we're trying
map
to
those.
fill out the pattern.
Fill out the pattern, yeah.
So mathematical physicists figured out that this pattern actually isn't just a collection of dots in a diagram. You can actually describe this using geometric, like continuous geometric manifolds, continuous surfaces. Okay, so now we have
like
geometric.
a checkerboard.
No, not like a checkerboard. More like things like circles and twists and knots of geometry.
But it's a continuous pattern, though.
It's a continuous geometry that ends up being described by these patterns.
Continuous geometry described by this pattern,
Right.
yeah.
So we know, and this is important because we know that space-time itself is like a smooth four-dimensional fabric that's wavy. Okay, and since we know space-time is accelerating in its expansion as we look out into the cosmos, okay, we know that space-time itself is sort of like a four-dimensional hyperboloid. Right, it's opening up, it's accelerating its expansion.
Yeah, the galaxies are all moving away from each other, yeah.
So how in the world does that relate to these particles zooming around? Well, it turns out
That's
that
something to do with dark energy, though.
it does.
Yeah.
Yeah, that's right. So it's
Moving
dark
apart.
energy that exists and allows the acceleration of expansion of space. So it turns out that all these particles that we're describing in this diagram, these correspond to a smooth shape. And when you include the gravitational description in terms of how do you describe the gravitational charges in terms of this smooth shape, you see that the only consistent way to do it is with this infinite extent geometric pattern that includes this hyperboloid inside it. So this pattern corresponds to this wonderfully complex, smooth, high-dimensional geometric structure that is described by this pattern of charges. But it's actually the geometry of this structure itself that's really fundamental. And I think, although people go back and forth on whether when you have a successful mathematical abstraction that seems to match up with reality,
Yep.
how much reality do you ascribe to that geometry itself, to the geometric structure? And I think our universe is this mathematical structure that's come to life. Yeah. And although that sounds wild, I mean, for the most part, using these sorts of geometries to describe elementary particle physics, this is standard particle physics. Okay, these geometries called Lie groups, and the way of describing them and their curvature over space-time as gauge theory has been known to mathematical physicists since the 50s.
So this is the fundamental way of the universe, kind of.
Yeah, the universe is fundamentally geometry.
Fundamentally geometry, this geometric, this math and geometry that's going on replicating itself throughout the fabric
That's
of
right.
the
And
universe.
it's doing it in a quantum mechanical way, such as exploring all possible paths at once. That's our best understanding of it through known physics. And what I do is a little more unusual, which is this structure and this description of reality seems sufficiently coherent, and it all appears to be part of just one mathematical structure, which to me is very compelling.
Yeah.
So I found this matchup in 2008, or 2007, I guess, late 2007, between the known structure of elementary particle charges and their interactions, and this one mathematical structure called the E8 Lie group. And this is sufficiently inspiring that I've worked on this for a number of years. And more recently, I've been trying to come together with a natural quantum mechanical description of the theory, which has been pretty wild itself. Yeah, because what nobody has done is come up with, even though we've described everything in terms of geometry, in terms of smooth structures, quantum mechanics is always something that's sort of added as something put in by hand to take a classical theory and a classical geometry and then apply the quantization procedure and get a quantum description. That's something that's always done by hand, but the universe can't work that way. The universe is fundamentally quantum mechanical. So if there is a fundamental structure that describes the universe, it has to be a quantum geometrical structure. And that's what I've been after lately. Yeah.
Okay, what is this quantum geometrical structure?
Well, as if things weren't complicated enough. So when you're considering the geometry that describes this pattern, it's you end up with a 248-dimensional twisted up structure. But quantum mechanically, right? Each one of these points in this structure corresponds to just one particle, right? But when you do quantum field theory, you can have multiple particles of the same kind at any space-time point.
Oh, geez.
Right? So if you're going to have a geometry that describes that in a consistent way, quantum mechanically, you have to have an arbitrary number of these particles at every point.
Yeah.
So you don't have, even though 248 was a ridiculously high number of dimensions and a high number of particles, in order to consistently have a description of quantum field theory that matches reality, you have to have an infinite dimensional geometric structure. And when you have multiple particles at a point, that's different levels of the structure being excited at that point. But it turns out mathematicians have expanded on these finite dimensional Lie groups, and they have explored infinite dimensional Lie groups in their representations. And this is much more recent research, starting in the 80s or 90s. Okay, and there's actually a professor here at Berkeley who's pioneered the use of these, the description of these specific infinite dimensional Lie groups that I think best apply to describing quantum geometry.
Infinite dimensional Lie groups.
Yeah.
Describing quantum geometry.
Yeah, I think that's what the universe is. But this is new stuff I've been exploring, and it just looks extremely promising. But yeah, I think this is fundamentally what our universe is it's one of these beautiful infinite dimensional Lie groups undergoing excitations.
Yeah, excitations, yeah.
Everything we see is the result.
Yeah.
Yeah. And the thing that gets me about this is sort of the inevitability of this being our universe. Because when you look at these mathematical structures, you don't have, I mean, you can sort of dismiss some of the simplest one that wouldn't give you rich enough behavior. But if you pick out the richest ones with the most complex structure, you end up with, you know, a very small selection of possible realities that we could be in. And that just comes from pure mathematics. If there's some alien race in some other galaxy in the observable universe that's worked out high energy physics and mathematics, they're gonna see these same mathematical structures. Any advanced alien civilization is gonna know about Lie groups just purely from abstract mathematics. Yeah, it just comes out of pure math.
As in the fabric of the universe is like this across the universe.
Not only from our astronomical observations, we can tell that the universe is homogeneous, that things appear to be the same at far distances, same laws of physics, from seeing how stars and galaxies behave at huge distances. Not only that, but just abstract mathematics itself, when you start with the integers and then the real numbers, and then abstractly describe smooth surfaces. What can smooth surfaces do? How can they tie into little knots? When you go along that path, you hit this description of Lie groups and things that are special about Lie groups. And they have all sorts of unusual characteristics that you wouldn't guess, but any civilization working out this mathematics is going to hit them. It's going to know about them.
What happens when we tap into the quantum geometry, into the understanding of the Lie groups to its fullest?
In terms of practical applications?
Yeah.
I have no idea how it's going to go. I don't have any more idea of how it's going to go than the first people to start thinking about atoms existing.
Yeah, okay.
Yeah, because it's first you have to find it, figure out what it is, and then it takes 50 to 100 years of engineering before you can manipulate things on that scale.
Yeah.
And then make use of it. Yeah.
Maybe that has a tie into nanotechnology.
It would be beyond nanotechnology.
It'd be beyond nano, but maybe that could then help with nanotech to be able to just throw up a little sphere and have it turn into a car, and then just have it compile back into a sphere.
I can't even speculate what's going to happen. You are going to need large amounts of energy to manipulate things on a tiny scale of that level. So you're going to have to use stars and pull them together to create black holes, and use arrangements of black holes to create sufficient to manipulate particle beams in such a way to manipulate things on that scale, because you need enormous energies to get down and access and tinker with things on that scale.
Can't fusion provide that?
Well, it might.
Okay.
Essentially, that's what a star is. It's a huge fusing mass of matter.
Yes.
So in some degree, yes. But the thing is in the same way that the first atomic bombs were made by taking fissionable material like uranium or plutonium and surrounding it with basically dynamite and compressing it inward with the explosion of the dynamite to kick off the fusion bomb. It's the same thing. You sort of lever up in energy. So who knows what we'll have to do to create the power to manipulate things on the tiny scale. But it's centuries away from us. But I'm not driven by practical application. I'm driven by wanting to understand what the universe is.
The discovery. Yeah. The discovery. I'm driven by both the discovery and the practical application.
Yeah.
How many times have you looked at this and cried?
It wasn't sad. When I first saw this thing, it was more like an orgasm.
That's what I mean. It's such an orgasm that you cry. It's like I like cry when I see things.
I'm learning too much about you, Alan. No, it was a very exciting moment just to see that these structures underlying particle physics are actually this pretty.
Yeah.
Right? You don't expect it. I was playing with matrices of variables interacting with one another through linear algebra. And to go from those matrices to find out that, there's all this beautiful structure behind it, and actually see a visual representation of this pretty structure, and to see all the interconnections between everything appearing in these amazing mathematical structures. That was mind-blowing. Yeah. I had to take a moment until the excitement had worn down enough that I could go back to working on it.
Yeah.
Yeah.
Exactly. So looking at this with me for a minute, one of these elementary particles is the Higgs boson. And then...
Yeah, actually, it's This one.
That
the,
one?
The square ones are the Higgs.
The Higgs. Okay, cool. So now.
And if you end up packing the larger pattern, you can see how they interact with all the particles to give them their masses.
Ronnie, will you pull back up the?
I don't think he has control of that.
Which one?
Yeah. So if you freeze it.
Okay.
Yeah. So if you pick one of these Higgs bosons, you can see like if you add this, right? So if you take this distance from the center to this Higgs here, you can add that to this one to get that one.
Oh, so this distance is equal to that?
So you take this as a vector and you add it, and you get that.
Yeah.
So this is the Higgs interacting with this quark to give that quark. So the charges all have to conserve. So it's just vector addition when you do the charge conservation.
So when they all overlap, like when we see them like come together and then go back out, when that happens, that's the superpositioning of the particle?
No, it's just an artifact of the projection.
It's an artifact of the projection.
Right,
Okay. Because it's on a two-dimensional.
But when you do the vector addition, so if you...
Because you said it was 248.
Yeah.
Yeah.
Well, but this diagram's only 8 dimensions. So but if things have to satisfy charge conservation along all 8 dimensions, okay, so you take a vector from here to there, right? And this is a vector.
Yeah.
And you add it, and you get the same vector between these two particles.
Yes.
Okay. When you take that and you project it down to 2 dimensions, you'll end up with a 2-dimensional vector, and that'll still equal the other vector because the projection conserves the charge conservation. It preserves it. Yeah, so that's why you see it as the same lengths on here. Yeah. So you can actually look at this 2-dimensional diagram and see all the allowed interactions, which is pretty cool. Yeah. But it's a really I found it to be a really enlightening way to describe elementary particle interactions.
Yep.
There's some things that are harder to capture. So we know that all these particles have different masses, and these masses aren't charge. Okay, the masses aren't quantized. They don't behave as charge. So it has to be, those masses have to be coming out with from some other aspect of geometry, which nobody knows how to describe yet.
They all weigh different amounts.
Yeah.
And we're talking like on the scale of like.
Well, so for every known elementary particle, like an electron, it has 2 more massive partners. So called the second and third generations. So an electron has the muon and the tau, and these are other elementary particles that appear to have the same charges, the same electric, weak, and strong charges, but they have different masses. And nobody knows why that happens. So what has to be happening is, since the Higgs particle is interacting with these to give them their mass, it has to interact with these other particles in a different way to give them different masses. And the masses are like, they're off by a factor of 100. They differ by a factor of 100. So as soon as these more massive particles are created, like a tau gets created, it's instantly gone, and it changes into less massive particles. Okay, so a tau will immediately decay down to a mu and kick off a neutrino and an antineutrino, and then from a mu down to an electron.
So then there is a tendency for the elementary particles to move based on the weight of them.
Yeah, it's their masses dictate what can decay into what can change into what. But we don't know. We don't have a good description right now in physics of why they have the different masses. It's a big mystery.
So the elementary particles are also decaying and
yeah,
moving
they're
based
changing
on
one
masses
into the other all the time. Yeah.
Even in this field
Yeah.
right here.
Every interaction is a particle changing into another 2 particles.
Every interaction.
Or 2 particles coming together and making one.
That is every interaction.
Every interaction. Yeah.
Is particles coming together to make
a different particle.
And a neutrino.
That's another kind of particle.
Yeah.
Yeah. So
it's so interesting. There's when we sat down with Clea Irwin as well. There's never been a time that I felt, and the same thing goes for you, more like explain like I'm 5 on the show than on the shows about physics and particle physics.
5-year-olds love Legos, so
love Legos.
Lego
that's
analogy
a great
works
way
great.
to put it.
Elementary particles appear to be the Legos of our universe.
Yeah.
Yeah. And they each have different. Their charges correspond to their the Lego shape. How many pips it has. and what other Legos it can attach to.
Because not all elementary particles can attach to other or
No, they have to be they have to have
they
compatible
have
charges.
compatible charges,
Yeah.
and those other variables. There were like 5 of the other variables.
They're all charges.
They're all charges. All right, thank you, Ron. Sorry, 15-minute timer. All right, so let's talk about PSI a bit as well. I want to show some of the other beauty. This is amazing. Whenever my mind gets expanded to new dimensions of thought, I freaking cry. I cry, and I feel this just insane ethereal feeling that can't even be described. But let's talk. So PSI, and I'm excited to show some of the content that we have lined up here. What would be a good? Let's start with maybe the drone shot of the.
Sure.
Yeah.
Well, I mean, I came up with these physics ideas in 2008, and at the same time, I was supporting myself by investing, and I had been traveling around through different friends' houses while I was doing the work. And what I found is it's really easy to work on stuff while you're living in friends' houses.
Yeah, exactly.
Because you're not worried about having to fix stuff. You're not living in your to-do list.
Yes.
The way you are if you own a house.
Yes.
And you're thinking about all the stuff you need to do. So I was able in my
You're more relaxed. You have more
Yeah.
time to be able to do the research and yeah.
So I had been traveling around for a decade since getting my PhD, basically living in friends' houses while I'm doing this work in physics, or renting places, and investing my money as best as I could. But after a decade of this, I wanted to make it a resource available to other scientists.
Yep.
I wanted other scientists to have the ability to go to some nice place
Yep.
and just hang out there and not be told what to do, but to work on what they wanted to work on
Yep.
while they stayed somewhere beautiful. And so I got the money together and got $500,000 put down on a decent little ranch house in Hawaii. A friend of mine helped me build some little cabins. And so now we've got a few bedroom cabins in this fairly modest property in Maui. It's a nice location.
This is going to show us the cabin shot now.
Yeah.
On the way down. So
So a
we're on
friend of mine and
Maui
I
here.
built these
We're
little cabins. Yeah.
on Maui, about 20 minutes out from the beach, driving. Your friend came and helped you put these together. These cabins. There's 4 of these cabins. And they're right on the same property, and you were inspired by your kind of like your freedom. You had freedom with your time and you wanted to provide that to other people.
Yeah. So it's a great little environment. I mean, people come out and hang out anywhere from a couple days to months, and it's a nice little scientific community on Maui. We also go on trips to the beach, surfing, kite surfing, paragliding, lots of fun stuff to do around the island.
We have that video of kite foiling. By
Yeah,
the way.
let's do it. Let's showcase that video because that's also exciting.
Yeah, Maui's it's just a beautiful place to hang out and play.
This is gorgeous. This is Earth. This is Earth. This is the beauty of Earth. This is 20 minutes away.
Yeah.
Yep. It's amazing.
Yeah. So basically, I wanted to. Science has given us
nature. You wanted to give us also the ability to tie right into nature right here in Hawaii at the same time as you're doing the science. Yeah.
And science have given us the best tools and the best progress mankind has achieved. And it's really due to scientists working on this stuff. And they're not always compensated as much as they should be, given how much they're benefiting humanity. So as a personal philanthropy, I feel that one of the best things I can do is try to make life better for scientists. And the best way I've found to do that is give them a nice place to stay and work without any stress, and hopefully they'll come up with more good stuff.
Yeah.
Yeah. It's also really fun for me on a personal level. It's very satisfying to be able to have a bunch of smart people coming through and
exactly.
playing around on the island with me.
Exactly.
Yeah. And this is some of the more fun I've been having lately is hydrofoiling with a kite.
Oh man, look how fast you're going because you're not riding any waves.
There's very little resistance. It's a very efficient craft. And you're just using the kite to pull you, and you're zipping along the water. And you leave almost no wake because you're not smacking the water.
Exactly.
You're flying through it with a carbon fiber wing.
Yep.
Yeah,
Yep.
It's wicked fun.
Oh, that carbon fiber wing. Yeah, you're just standing on top of the board. The wing goes down into the water, and then that was such a smart invention.
Yeah, if someone had described it to me I would have said, there's no way this is going to work. It's going to be too unstable. And it is unstable, but it's manageably stable.
It must be, very unstable. Yeah, manageably, yeah. Yeah, I bet it's very unstable.
Yeah. It doesn't want you balancing on it.
No, no, exactly.
Yeah, but with that opposing force of the kite acting
Yeah.
as a sail, and then with the foil acting against it, it's
Yes.
just,
It's just stable
just-
enough.
Yeah.
Yeah. And you're going what, like, you're going like, what, 20 miles an hour?
Yeah.
Yeah, that's
20,
awesome.
20 or 30 knots. Yeah.
Wow. I mean, this is the life, being able to. It's the life. Yeah, it's the life. You're a smart man for wanting to, build it on one of the most beautiful places in the world, and also provide people, like you said, with that time, with that ability to come in and really just be able to focus on what they want to do and relax at the same time with nature. I think it actually produces more effective results when you're able to go to the beach 20 minutes away from you.
It's wonderful just for clearing your mind, and I think there's just to be able to focus your eyes on beautiful scenery
Yes.
20 miles away.
Yes,
I think that's not only good for our vision,
it's very good for vision.
right? But I think it's good for our souls.
For the soul as well. Yes, so good for the soul. To actually just, be in the ocean and to be smelling fresh oxygen, inhaling the fresh
Yeah.
oxygen. Now, let's pull up the other, you have the not hang gliding, paragliding, right?
Yeah, Maui's basically a playground in paradise. I mean, it's just spectacularly beautiful, and you can
Wow.
choose to go out and do something fun every day if you want to.
What is that?
Those are the West Maui Mountains. So right now I'm standing on Haleakala, which is the main 10,000-foot mountain.
Yeah, yeah.
And then this is a view from about 6,000 feet. And then Maui is basically a big valley between that mountain and the West Maui Mountains, which are at about 4,000
Wow.
or 5,000 feet. So you're seeing pretty much the whole island right here.
This is just an unreal video. Look at how those clouds are just perfectly right in front of the other.
It's a ridiculous place. It's a ridiculous place.
It is such a ridiculous place. Wow.
Yeah.
So lucky that
And
Hawaii
this is one of the
with
most
us.
consistent paragliding launch sites in the world. You can do this pretty much every morning. And it's a 20-minute drive up from
Really?
PSI. Yeah.
It's a consistent.
Yeah.
Oh, that looks amazing. And so you bring a parachute with you too,
Yeah.
just in case.
A paraglider fits into a backpack.
Yeah. Okay. Yeah, but then you're wearing a parachute. As
Oh yeah,
well,
you have a reserve chute on the
a
harness.
reserve chute.
Yeah.
And then.
But you're usually too low to deploy it.
How do you get to like?
You drive up.
No, but how do you get to ensure that you like stay up above the tree line and not like go down?
You start with a steep enough slope. You
Yeah.
fly out away from the slope.
Yeah.
And then the idea is if the sun has heated up the earth enough, it'll kick off updrafts, thermals.
Updrafts, yeah, thermals that come
And
up.
so
yeah,
you,
yeah.
you fly into these thermals, and you have a variometer that tells you whether you're going up and down. So you hit a thermal, and then you start going up.
Yeah.
And if you hit one, and then you start spiraling in it and ride it up.
Yeah, yeah, and then you can go right and
Yeah,
left.
and then you get higher, and then it peters out, and then you go looking for the next one. And as you're looking for the next one, you're dropping, but then you find another one and ride that one up.
This was really great footage as well. These
Oh,
are
thanks. Yeah, I remember that wave. I didn't quite get my head in tight enough.
tight enough on the head. But
Yeah.
look at how it looks from the bottom as well. You're riding, what was that, like a 10-foot wave?
A little smaller than that.
8?
Yeah.
Yeah, that's so sweet.
I mean, a Hawaiian would call that a 3-foot wave because they have really big
Hawaiian.
feet.
Yeah, Hawaiian would call that. Okay, so we'll have links for PSI in the bio. You go stop by and go hang out with Garrett. Definitely have to go hang out with Garrett. We'll be there too. If you guys help us out on Patreon, we will go there and interview the brilliant scientists there, and we will get our butts there much faster, and we'll be able to produce better content for you and work on our creativity, work on.
So really, for the
Yes.
betterment of mankind, send Alan to Maui.
Yeah. And Ron and Alfredo, let's get the team out there. And so that's PSI. Now I want to ask you a couple questions that we typically ask on the show. The first question being, there seems to be a lot of wealth that's being concentrated in the hands of very few. and then and that's being exacerbated by exponential technology, and then the very lowest of socioeconomic classes are going up just very slightly.
Yeah.
What do you think about that?
I think that it's a struggle, and a lot of the infrastructure and social systems that are in place are there to enforce that. They're there to make sure that the poor stay poor and that they don't grab resources away from the rich. So we're always sort of, so the wealthy sort of play this game where they're trying to concentrate and grow and maintain their wealth. And if too many people climb up to their level, that often takes away from them, chisels away at it. So they try to make it the game, so it's very hard to do that.
Yeah.
Whereas technological progress sort of floats every boat. All right? So as technology progresses, that does increase quality of life for everybody on the planet. Okay? So as long as you're not worried so much about people having it better than you, then your life's getting better, more than likely. But economically, just the way capitalism works, wealth is able to accumulate and grow more wealth. So capitalism is always sort of at risk of being too harsh on the less well-off. And if you're really too harsh on people who have it bad, they're going to rebel. They're going to pick up guns, pitchforks, bats, whatever, and just wreak hell on your property and on your life. So the wealthy are always playing this game. It's like, well, we don't want to be too bad on them because then they'll rebel and our quality of life will be bad. But I think it needs to be better than that, because I don't want to live in an environment where people are peeing on the streets. Right? I don't want to live in an environment where there's sick people wandering around that need help and aren't getting it. Personally, even if it costs me money, I'd rather live in a society that takes care of its poor, and so that my environment is better. It's purely for selfish reasons. Purely for selfish reasons, I don't want a bunch of people being poor. I want everybody to have healthcare available to them who needs it. I'd like everybody to have at least a subsistence amount of food and shelter provided to them at the bare minimum. And as we have more and more technological increase, especially with computers being able to do more, there's going to be fewer need for the labor of humans. And so there will be more and more people who can't get jobs. And just for purely inevitable reasons, I think we're going to have something like a universal basic income for people. And keep in mind, I'm mostly a libertarian. I just want the world to be as good as possible so I can enjoy living in it. But that means making life decent for everybody.
We were just talking about this at the Blockchain Economic Forum yesterday, our interviews, that there's never going to be a ceiling. We never want to put a ceiling up for wealth, accruing wealth. But a very bare minimum, how we do that, funneling money down, you want to teach people to fish, right? So you want to give them access to these information highways that enable them to be up at this bare level, every child being born into the world, having access to all this opportunity at least. How do we balance the we are one mentality with geopolitical leadership?
We have to not go backwards. So there is a pull to go backwards, and we just saw it in this last election. I mean, the election of Trump was a step backwards. I mean, we were heading towards a more progressive, being a more progressive nation, where we were getting along better with other nations. We were providing more for the less fortunate in our country. We're providing more for the middle class. But the middle class and the lower class decided to take this step backwards, where they wanted like a stronger, more egomaniacal, conservative leader in place, who they thought was going to make our interests better, make U.S. interests better, at the expense of our foreign neighbors, and apparently at the expense of everything except the corporations and the people who own them. So I think Trump is a great president if you're a large shareholder or running companies. He's even great if you're doing a bunch of scientific development in the medical field, because he's big about deregulation. But if you're poor and need medical care, it sucks. So I think what I've been saying is Trump is great for corporations and lousy for people. But I think we're going to see the pendulum swing back, and I hope it doesn't swing back too much, that it hurts corporations so much, because I do think it's capitalism that's driving progress in our society for a large degree, and I don't want to slow it down.
Definitely. Do you think that we are alone in the cosmos?
If you mean, are we alone and that there's nobody else out there, sentient beings like us? No, I think the universe is so vast and life so ubiquitous. I think there's many, many other advanced civilizations out there in the universe. If you mean, do I think we're alone and that nobody's talking to us? Yeah, I think we're alone that way. I don't think there's been any contact between any alien civilizations and Earth. Yeah.
What do you think is roaming throughout these galaxies?
Who knows what's out there? I mean, space is not very hospitable to meat. So I think what most likely happens is some civilization reaches an advanced enough degree to make cool, intelligent things out of metal and launch them into space. Mm-hmm. So I think lots of probes go out that are basically synthetic intelligence with metal bodies, and they go out and explore and colonize and communicate, and it becomes largely a spacefaring, if you want to call it a synthetic intelligent automated civilization.
Hopefully you can just put consciousness onto those probes.
Yeah, at a suitable level of technology, yeah, you'll be able to upload consciousness into whatever
No, I just want
material
to
substrate.
Teleport right into the other world areas.
It's gonna be a party.
A party?
It almost makes me regret being born this early. Right? Because I think the future is going to be pretty fantastic in what humans are able to do.
Yeah.
I also have to admit I'm a little bit resentful that I feel like I'm going to die right before we have really effective longevity, life extension.
Yeah, yeah.
Because there's a lot of progress being made right now and a lot of research now just starting to get supported.
Yes.
In extending not only quality of life but also duration of life.
Yes.
And I think that's going to be a revolution in our society, and I think it's great. But
we'll
I think I'm just
carry the torch of PSI.
Yeah, I think I'm going to miss it. I'm going to be sad not to be there.
We'll carry it,
because the future's going to be great.
Hopefully, you'll be rebirthed into. You've done a lot of great work, so into something even better. Who knows?
Yeah, but there's a Woody Allen quote. I don't want to live on through my work. I'd rather be known for living on in my apartment.
In my apartment.
Yeah.
Okay, and then how about? Do you think there's a designer to the universe?
No. I don't think there needs to be. I mean, as far as I can tell, this universe is some pretty mathematics that's come to life, and there's nothing about it that. If you're going to design a universe, you're going to make one that looks more like Conway's Game of Life, right? Where it's a checkerboard and you have things interacting on the checkerboard and progressing, and you get complex structures there, and you can get very complex interacting systems with some very simple, discrete, classical rules. And our universe is nothing like that. Okay? Our universe is a wonderfully complex mathematical structure, and it's evolving quantum mechanically, and quantum mechanically it has an infinite number of degrees of freedom. Even if space itself was discretized, even if it was a checkerboard, which it's probably not, okay, you would still have an infinite number of degrees of freedom and infinite probability variations for how everything's evolving. So if you're going to design a universe to be simulated on a computer, you wouldn't design this one, right? You'd have a universe that was much simpler to simulate. If this is a simulated reality, it's a reality being simulated for some purpose that is simulating a reality sort of like the one that's doing the simulating.
So we can analyze the progress and see how it does.
Except there's been no indication of any influence by whatever might be simulating this reality.
Truth.
So given that that's the case, effectively from a scientific viewpoint, it doesn't matter. It doesn't matter if this is a simulation or not. Maybe it is, maybe it isn't. Also, I mean, there's a probabilistic argument for why this is a simulation. We might be in a simulated reality because a sufficiently advanced civilization can simulate realities, and we expect there to be many advanced civilizations in the universe doing many simulations. So given that there's only one universe and many simulations, it's more likely probabilistically that you're in a simulation. That's a fairly compelling argument. However, we only have one case to go on. We only have the one data point. We could be in a very unusual situation And since we only have the one bit of data to go on, you can't really make reasonable statements about probabilistic distributions when you only have one data point.
And our last question is, what do you think is the most beautiful thing in the world?
It's hard to beat a really beautiful breaking wave when you're in it. It's just such an amazing experience. I really don't know anything better than that. Right?
There it is again.
So, yeah, when you're doing that, it doesn't get much better than that. It'll make you mortgage your house, sell your stuff, and just spend ridiculous amounts of money on fancy surf trips. Yeah.
I love it. That's so beautiful. It is riding the waves of the earth. I also said that riding down the slopes of the earth for skiing or snowboarding.
Oh yeah, snowboarding's fantastically
that
fun.
kind of stuff. Paragliding, paragliding. Again, just that was some of my favorite moments. Was after you skydive, then you're just sitting there in your chair, just gliding through.
Yeah, paragliding. If you like that part, you'd like paragliding because it's all that part.
It's all that part.
If you're doing the other part, the free fall part, while you're paragliding, that's bad.
Yeah, you never want to get there. What a thought-provoking show. Thank you so much for coming, Garrett. We appreciate it so much.
Oh, no, thanks for having me out here.
Yeah, this was so enriching. I feel like I understand elementary particles 0.00001%. I feel like at least there's that. Okay, great. Well, there was a lot of good wisdom here communicated today. If you guys had a good time, make sure to share what you learned with 2 people. They'll go share what they learned with 2 people, so keep doing that. Join us, subscribe, comment below with your thoughts. Don't just consume this content, go create with it, make a video, make a post, go talk to your mama, your papa, your uncle, your sister, your cousins, go talk to them all about it. Also join us on Patreon so we continue doing cool things like increasing our studio space, making better content for you, more live events, going to the Pacific Science Institute, highlighting smart people out there. Much love, everyone. Thanks for tuning in. Thanks, Ron, our producing partner. And we'll talk to you soon.